Good afternoon. You all know Simon's a professor at New Jersey Institute of Technology. He has an amazing breadth of information and knowledge with a very, very high interest in a whole variety of places, consulting to the broadest spectrum of clients you can imagine, many you can't. All related to all how it is put together, this very complex thinking about swarming and all its relationships and all its applications. So, Simon.
Can you hear me? All right, perfect. How are you? Yeah, nice. All right. So when I was invited to come to this, that could have been the title of this talk, because I'm not a conservationist, I'm not a person involved in sustainability research or any of the topics that seem to be the prime core of this conference. But David earlier, where is David? Maybe he's gone already, pretty much set the tone for the entire talk that I'm going to give. It's all about connection and how everything is connected together. And I'm going to show this through essentially some of my research on swarm behavior and also some of the research of other people on how swarm behavior works, but also fails miserably in a lot of occasions. So don't expect a very happy story. It's a story with ups and downs. All right, so I'm going to start by introducing myself. I'm a biologist, but among the biologists, I'm a bizarre biologist. You can find me sometimes in the fields in the tropics. That's the tropical forest of Barro Colorado Island in Panama, where I spend most of my time not looking at bats, but looking at the ground for ants. But I also do a lot of work in the lab. So you'll find me sometimes holed up in my lab, studying this very fantastic organism that I know you're going to discover in more details tomorrow with Heather, which is the slime mold Physarum polycephalum. I'm not going to talk about it today. I'm just going to show you this. You have to go to the workshop tomorrow to know what it does and why it's so fantastic. But I'm also a little bit of a theoretician. That's just a sample of 2 pages of a paper I published last year. I don't know if you can see, but out of this, there's something like 60-something equations in this paper. I don't remember most of them, so I could not explain them to you. But it's just to show you, I do field work, I do lab work, I do theory, and I'm also a little bit of an engineer on the side, where I do bio-inspired design, working with people in robotics, engineering, computer sciences, particularly working with tiny little robots that are pretty stupid on their own, but then can sometimes do fantastic things together. Okay? All right, so I'm a sort of a jack of all trades. I like to say that I know very little about a lot of things. But if you want to really know what a biologist does in his work, you have one single question to ask that biologist is, how do you define life? What is life for you? Okay? If you're an evolutionary biologist, life might be, you might be in agreement with Ralph Waldo Emerson's definition of life, which is the creation of 1,000 forests in 1 acre, which is probably the best definition of evolution by natural selection that I know of. If you're a biochemist, you might agree with, I can't pronounce this name, so I'm not going to try to pronounce the name of that person, but life is nothing but an electron looking for a place to rest. If you haven't taken a biochemistry course, it's all about energy exchanging within the cell, right? Now, my second favorite definition of life is by the astrobiologist Mike Russell. The purpose of life is to hydrogenate carbon dioxide. Right? If you don't know what that means, it's all about entropy. It's about the idea that living systems are essentially, the purpose of life is to increase the rate of entropy increase in the universe. You don't have to believe it, you don't have to accept that definition, but it's actually not completely false. Now, my definition of life is a little bit different from that. It's more maybe practical definition of life, if you want. For me, life is a perpetual experiment in problem solving. And by this, what I mean is that, right, organisms face problems every day in their life. Problems are are limits to the organism's fitness, to its ability to survive, to reproduce, and therefore to evolve over evolutionary times, and solving essentially any non-random mechanism, structure, process that will overcome or pushes back that particular limit. Okay? So that's the way I see life. I see it from the engineering point of view. I want to understand how do organisms essentially solve the problem that prevent them to be more efficient in their daily life, prevent them to be more successful from an evolutionary point of view. Okay, so if you want, there's two kinds of biologists. There are those that try to build things, and there are those that try to destroy things to look how it works. I'm the second kind. I take everything apart just to see how it works inside, and then I don't try to put it back together. Okay? Now, the type of problem I'm interested in particular is this particular question, is how do many simple parts, often parts that by themselves could not do much, like the neurons in your brains, how these many simple parts can combine their efforts together to create one complex structure capable of solving very complex problems, right? Think about what your brain is capable of doing, and now think that it's made of billions and billions of tiny cells which individually are pretty much incapable of doing anything. Right? If you take a neuron, you put it in a petri dish, nothing happens. Nothing. It just stay there and die. Right? That's the big question that I'm interested in. How do we take many simple, often stupid and useless parts, we make them work together, and they become one complex and one beautiful and functional structure? Okay? Now, we've talked about birds, so I decided I'm going to put a video of birds, because bird flocks are one of the most beautiful things in nature, in my opinion. Not the most beautiful, one of. And one of the main theories that I think is driving all this ability from one system to become a complex structure and complex functional structure is a theory that dates back to the 1950s, coming from theoretical chemistry, which is called self-organization. Have you heard of self-organization before? Yes? But have you heard of self-organization outside of like a union context? I'm talking about self-organization in nature. Yeah, you know. All right, so self-organization. I have one video that I'm going to show you. This video explains everything you need to know about self-organization. Be very, very careful. Don't miss anything. It's also the cutest video you'll see today. All right, so if you're allergic to cuteness, just comes out. Wait. Self-organization. It's a system in which you have agents, particles, that are in a disorganized state. These particles, through some mysterious force, You done laughing? I was trying to give you an explanation here. So through some mysterious force, these agents enter an interaction, and through these interactions, a form of organization emerges at the collective level. You want to see it again? Here you go. Look at that. Puppies, milk, that's all you need to explain self-organization. Again. You can find it on YouTube. Just type Scotty Pinwheel on YouTube. Scotty Pinwheel. That's the title of the video on YouTube. All right. So self-organization, essentially everything is about interaction. Everything is connected, as David mentioned in his earlier talk. And these interactions, what's very important is they can be very simple. They don't have to be complicated. In the case of the pups, the interaction is purely physical. They are just pushing each other. There's no need for complex cognitive processes happening here, right? It's purely physical in this case. The interaction can be complicated. They don't have to be. Right? The interactions are local in the sense that no single individual interact with everyone inside the group. Right? Each of the puppies interact only with its left and right neighbor, but doesn't interact with the puppy across the ball. Okay? So they are local, and by this local, again, it's an information context. They are local, and you don't know everything that's happening in the system. You just know what you can perceive. What's very important is they are repeated. These interactions are constantly repeated. If you prevent the puppies from interacting, then the collective organization disappears. Okay, so it's a system that we call far from equilibrium. It requires constant input of energy to be able to function. Okay, So it's very different from systems in chemistry or physics that tend to reach a lower energy point. This system needs to be constantly bringing energy. Okay? Now, you might have encountered this in your physics class. This is an example of self-organization between metronomes, just to show you that it doesn't have to be between living organisms. All these metronomes, all they do is apply a force on this board, and this force is transmitted to the metronomes that are next to it. And then the action-reaction of the metronomes and their interaction throughout this board here leads to a synchronization of this metronome that all started at different oscillation speed. Right? And you have videos on YouTube, and that's the one that's the clearest to see, but you can find videos on YouTube where they do this with 200 or 300 metronomes, and that still works. And it will work. It will just take a little longer, but it will always work. It's less funny than the puppies, though, right? But we have to have something that you can do in your classroom. You cannot have puppies in your classroom. Right? But this idea of synchronization is something we also do naturally. This idea of us being this oscillator that synchronizes. When you go to the theater at the end of the play or at the end of the concert, you clap, and at some point people start synchronizing. And this synchronization is exactly what the metronomes are doing. All you're doing is listening to the people around you or looking at them, and then you just adjust your own clapping speed to the clapping speed of your neighbors. And then if you propagate this throughout the entire room, at some point everybody is going to be clapping in synchrony. And if you don't believe that is serious science, this was published, you can't see it, but it was published in Nature in 2000. So if it's in Nature, must be very important. If you're not a scientist, you don't get that joke, I guess. All right. Now, what I want to say is self-organization is probably one of the fundamental laws in nature. Pretty much, I think it's, for explaining biology, at least as important as understanding natural selection. Right? And just to give you an example, so it's very important because it creates coordination. But it's also a very important theory because it explains how you can get complexity, right, complex behavior out of very simple units. So I don't know if you know this game, Conway's Game of Life. Never heard of it? So I'm going to explain it very quickly. It's very simple games, right? You have a grid, can be as big as you want. And on this grid, you have cells that are either alive, so that's these black and gray cells, or dead, the white cells, okay? A cell is going to remain alive, and a cell is going to die at the next round of the game if it has less than 2 neighbors around it. Okay, so if there's not enough neighbors around this cell, at the next stage the cell disappears. Okay? If a cell has more than 3 neighbors, it will also disappear. So think of this as an example where you don't have enough individuals around you, your environment is not good enough, and you will die, or that's an overcrowded environment. There's not enough resource anymore to share with everybody else, and then you're going to disappear as well, okay? And then you have these 2 situations in the middle. If you have 2 or 3 neighbors and you're an alive cell, then you're going to stay alive in the next stage. And if you're a dead cell and you have 3 neighbors, then you are born through the reproduction between these 3 cells. Make sense? So very simple rules, right? 2 rules decide if you die, 1 rule decide if you stay alive, 1 rule decide if you are born. That's it. Now, if you apply this simple rules to a very large matrix and you set the initial conditions for that system right, you can see this is all self-organized. There's absolutely no centralized control. Nobody is controlling here the emergence of this particular structure that seems to be taking a life of their own. Okay? This is a pure mathematical computer simulation, right? So Conway Game of Life, you have software online you can download for free if you want to play with them. Many of the situations are going to lead to just pure death of everyone, and we're going to talk about this later. But in some cases, you end up with this very, very complex machinery that seems to be producing, destroying, reproducing sometimes in sort of infinite loop in very complex behaviors that emerges from very, very simple rules at the beginning. So that's what I'm saying when I say self-organization is at least as fundamental to understand biology as natural selection is what natural selection explains how we evolve and constantly improve or adjust, adapt to our environment. Self-organization explains how we generate complexity out of simplicity. All right? You all good? So if you want to leave now, right, everything after that is just examples of how it's beautiful in nature, and then me depressing all of you when it, showing you how it miserably failed in a lot of situations. It's beautiful, right? These are just like white and black pixels, and I can watch this for the entire day. Now, this idea of self-organization has been studied for a long time in many different fields, but in biology and sociology it's been studied in the context of optimization, how we transfer information on social networks, division of labor, movement coordination, traffic organization, decision-making, etc., etc. And what I'm going to do now is I'm going to give you some example from our own research on how this thing is functioning in what is my favorite organism, model organism, the ant. I know I'm French, I have an accent, so I just want to make sure we are talking about the right type of organism. So that one. All right? We're all clear? All right. If you don't understand something when I'm saying it, it's probably because I'm saying it wrong. You have the right to correct me. All my students do it. They have a laugh at it all the time. I stopped being worried about that. All right, ants. So this is a video from a local from here, E.O. Wilson. You probably all know him. It's one of my favorite videos. Demonstrates something extremely powerful in ants. So these are ants. Their nest is somewhere around here. He's giving them a little bit of bread. He's going to put some food also on this side of the board. And in absence of any type of signals, the ants are just going to stay next to that first piece of bread. He's now going to grab a little ant here, compress its abdomen. By doing this, it's actually forcing the ant to exude a chemical, a pheromone, so a chemical signal. And this chemical signal, you can use it if you trace a little line with this little invisible ink. This line is actually a very powerful signal for the ants that will then follow that trail, follow that scent toward the food. So that thing, if you have a house, you probably have experienced the power of that scent in your house. This trail of ants, I'm warning you, this video lasts at least 2 or 3 minutes. This is an amazingly long trail of ants. But this trail of ants, right, this highway that goes all across the kitchen of this poor family, you can't get rid of that. I mean, you're done. This is entirely the result of that signal that E.O. demonstrated in the previous video, of that chemical signal, that pheromone that the ants are laying on the ground. I'm just going to let it go just to, it's like the disgusting moment of the talk. Think of what happened next time you leave your trash open in your... Right, it goes on, it goes on, it goes on. If the colony is big enough, it will go on for days. Right? Now, the reason for that is that this particular pheromone, this trail pheromones, ants have multiple types of pheromone. This one is a trail pheromone, has a particular effect. If there is trail pheromone, that is a positive feedback, which is going to essentially recruit more ants at the nest. These ants are going to reach the food source, lay more pheromone, that's going to recruit more ants, etc., etc. So you have a positive feedback loop here between the number of ants that reach the trash can and the amount of pheromone they lay on the path to their nest. And this positive feedback is regulated by 2 negative feedbacks here. One, which is the number of ants available for foraging. If you have nobody else available at the nest, at some point that number is going to stop growing. And also the evaporation of the pheromone. So the pheromone is a chemical, it will evaporate, it will disappear with time. And then that will also sort of combat this phenomenon. But if that phenomenon, this evaporation is slow, and then you have a lot of ants available for foraging, well, that's what you get in your house. And they're very happy ants. Do not kill them, I like ants. All right, so now, wait, not working anymore. Now, one very interesting thing about this pheromone, this is an experiment, this is a very classical experiment that I've redone back when I did my PhD. This is I'm just going to start again from the beginning. So you have an ant nest somewhere around here. There is a nice little sugary solution here. Ants love sugar, in case you don't know already. And then the way they can access this food source is through these 2 different branches, one being twice as short as the other one. Okay? Now, what you'll see at the beginning is, if you look at the number of ants on the left and right branch, it's about equal at the beginning of the experiment. But very quickly, you'll notice something. And here we go. Very quickly, the colony seems to be selecting choosing, if you want, the shortest of the two branches. And the reason for that is actually very simple. There's none of these ants, actually, these ants are Argentine ants. They are practically blind. They are extremely stupid, 200,000 neurons. Don't tell this to real entomologists. They will take offense. But the only reason why they choose the shortest branch is because it's faster to go this way. So ants that are coming back from the food source and lay pheromone, if they choose 50-50, the ants that have taken this path first are going to arrive here first. And so lay a little bit more pheromone here before the ants that have taken this branch can come and lay their own little bit of pheromone. Okay? So that's creating an imbalance here for the next bit of ants that are coming. All these ants that are coming after, they smell more pheromone here than here, and they naturally will take this path. Right? So this sort of combination between this very strong reinforcement loop that we discussed before and this difference in the timing, just the timing, that the ants need to be able to reach one end or the other, is enough to create this sense of collective decision making, if you want, an optimization of the shortest path between the food source and the nest. Again, none of the ants in this case knows what it's doing. Right? There's no central intelligence that is telling the ants that's the shortest path. It is the emergence of this selection is entirely the product of the collective behavior of the colony. Now, they can do this with more complex mazes. That's an experiment from my PhD, so a long time ago when I was young and beautiful, full of... Right, you can see that in more complex system, they will most often choose this path, which happens to be the shortest. Someone a few years after that did an experiment with 70,000 different paths possible between the food source and the nest. They still select the shortest one. It's pretty amazing. And it's so amazing that computer scientists are using this as a method to optimize short paths, to find the shortest paths within networks. For instance, to solve the what's called the traveling salesman problem, so finding the shortest path that goes through all these major cities in France without ever coming back to the same city twice, and while minimizing the amount of time it takes to visit all these cities. Okay, so you can use this optimization algorithm. 10 minutes only. Okay, I'm going to speed up because I have lots of things to say. Now, these pheromones, right? This is another example of these pheromones. Now, what they're doing here is they're actually creating a complete networks of these pheromone trails around their nest. And these pheromone trails are such that in some species, they will even remove all the vegetation out of it, creating like physical highway in the landscape. Okay, beautiful. There's leafcutter ants found in Central and South America. Now, this is not unlike our human settlements, with a central nest, if you want, and then peripheral roads radiating away from the center. Now, we used to be nomads, right? You remember that? You don't? Nomadism was actually a very, very successful strategy. These are just a cool video of Mongols. These created the largest empire, largest contiguous empire in the entire human history, right? So it's a very, very successful strategy to be nomadic. And some ants are also nomadic. They're called army ants. And these are ants you find in Central America and South America. They are called Eciton burchellia, Eciton hemetum are the two species we study. And these ants have a particularity. Every single night, they take the entire colony and they migrate the colony 300 meters away. Right, so 1 million individuals migrate 300 meters away every night. Now, the problem for these ants is that they don't have time to change the environment around them. Right? They don't have time to mold the environment to their own needs because every night they change location. And so they have a different adaptation. Instead of modifying the environment by destroying it, they use their own bodies to actually create bridges and structure that will allow them to move throughout this unknown landscape. Now I'm going to show you an example. This is from an experiment. If you remove the green background, this is the tropical forest behind. So this is an experiment in the tropical forest. And you see this bridging structure allow them to essentially keep an uninterrupted traffic along their trail. Even when the structure breaks, it can recover and rebuild itself. Okay? Beautiful? Impressive? Wait, it's only 2 rules to do that. One rule is, don't worry about the actual names, but essentially what it says is, as the structure grows and reach completion, the probability that you join that structure decreases. So if the structure is complete, no need to join it. And that's just showing you if the structure is used, the more the structure is used, the longer you remain part of the structure. Okay, so 2 rules. If I see a gap, or there is a gap in the path, I just stay there and I don't move as long as people are walking over me. Simple. In terms of engineering, for engineers, this is called a proportional controller. Essentially, an end has to decide whether it stays in or out of the structure. It stays in inversely proportional to how big the structure is. If the structure is already complete, there's no reason to stay in and you can go. And as a function of environmental factor like the traffic on the trail. Very simple mechanism, 3 boxes and a few arrows. Everybody can understand that. Now, that is what's amazing is that this is an experiment, so we destroy the bridge. It takes about 30 seconds to recover the traffic on that bridge, about 60 seconds to rebuild completely the structure. Right? So in 30 seconds, you destroy the structure, boom, the ends are back to normal. Try to destroy whatever fancy bridge you have here. We try to do this with the George Washington Bridge in New York. Didn't work very well. Now, one of the things that's also amazing is they can use this behavior to actually optimize the routes along the path to their new location. So the bridge started here, and as you can see, little by little, this bridge is essentially dismantling from the outer side and then building on the inner side. What's happening here is that the traffic takes the shortest path, as we discussed already, so these ends become useless, they leave, but we need more ends at the inside, and then the ends attach here, and then little by little, this bridge becomes suspended between these 2 platforms. Now, what's interesting is that this bridge is not going to go all the way. They never go all the way. They stop somewhere. Right? Stop somewhere. And if you're an ecologist, ecologists, if you don't know, are the economists of the real world, you think about cost and benefits. You're like, yes, there's a cost. Every time you build a bridge, you have to trap ants, and these ants are unavailable for other tasks. But there's a benefit, which is shortening of the trail. And then we showed in our experiments that essentially the ants manage to maintain a certain cost benefit. So what this experiment is showing, what this data is showing is what happens if you increase the width if you increase the angle here. When you increase the angle, it becomes quickly more costly to build a bridge, and the benefits grew in relationship slower. But if you have a really narrow angle like this, you can go very far until the cost outweigh the benefits, right? So there is a cost-benefit calculation that is embedded into the behavior of these ants. Now, I'm going to go quickly on this. We did some other experiments where we force them to walk. They come on this horizontal surface, and then we force them to walk on the surface that we can tilt. The result of that is if you look in the first 5 minutes, it should be falls per minute here. As you tilt it more and more ants fall from the structure. They're not really good at climbing, so the more you tilt the platform, the more ants fall. Well, the reaction of the ants to do that, that's experiments at the beginning, and you advance in the experiments, and you advance in the experiments, they build the scaffolding. Ants will start attaching and build this scaffolding that is, if you look at the side of the scaffolding, it matches very nicely the number of, the probability of the ants falling. Okay, I'm gonna finish. And essentially what that does is improve again the traffic and the pre-retrieval in particular by preventing ants from falling as they move through the structure. Now, okay, that's where I'm going to try to finish. Do you know Kurt Vonnegut's shape of stories? Yes? No? It's a great system to try to figure out how to build the story, right? The story has a beginning and an end, and then your story has to evolve between ill fortune and good fortune. There's multiple shapes of story. The one I've chosen to use today is what I call the boys get girl story, which is, boys meets a girl, fall in love with the girl, and loses the girl, then gets the girl back. It's like a story you've read or viewed multiple times. I made my own version for the scientist gets an ID. Right? I met an ID, science for organization, I fell in love with it, then I found a lot of issue with it, and now I'm here. I'm trying to figure out, can we get a better ID than that? Or can we do something to make it better, or will we be stuck with some of the problem I'm going to talk about now? Oh, not what I wanted to do. Yeah, that's my background. Tells you a lot about my own personal views about the world. Right, so we are here. I'm going to take you here now, and I'm going to leave you here. Right, I'm not going to bring you back here or here because I don't have the end of that story. Right, now, one of the big problems with this self-organizing system is they often have many undesirable collective output, many undesirable steady states. And I pulled this out of a paper that was published this year in an astrobiology paper. This is the results of a modeling work, where what they model is the state of the environment in red, if you want the temperature in the atmosphere, for instance. So lower is better. So you want to keep the red curve as low as possible. And in green, it's the human population. In this model, all you have is interaction between the environment and the human population. As the human population grows, it impacts the environment negatively. As the environment gets negatively impacted, the human population gets negatively impacted as well. Right? And what they show with their model is that there is only 8 possible scenarios. Whatever the parameter you set in the model, you'll end up with one of these 8 possible scenarios. Out of these 8 possible scenarios, 1, 2, and 3 leads to total annihilation of the human race. That's the happy story, right? Then 1, 2 of them leads with a scenario where the population shoots up and then a lot of people are going to die until we reach some sort of steady state agreement with our environment. Some of them are terrible. We end up with a situation where we have population growth and death, growth and death, and growth and death, and this kind of situation. And out of all these 8 scenarios, only this one is actually one we would like to achieve. Right? Now, just to let you know, we are somewhere along the growth curve here. But we don't know in which of these 8 scenarios we are yet. Right? Hopefully we are in this one. If you're a hopeful person like me, you think we are here. If not, pick your poison. All right. Now, what I want to show you is that these problems happens in pretty much all the self-organizing system. You remember this video? You remember this diagram? All right. Now, I'm going to just remove that little thing here, that little row. All right. I remove the regulation here. This is what you obtain if you remove that regulation. All right. This is essentially what you have here, ants that are following each other. So I've literally removed that thing, that regulation here, because essentially there's an infinite amount of ants that are available to reinforce the trail, and then reinforce the trail, and reinforce the trail. It's very, very wasteful. You read things in the literature saying that, in the general literature saying that they do this for days and die. I could never find any scientific account of that. I've seen it. It happens, and then it disappears after an hour. So don't worry, they don't die. But it's extremely wasteful. And the other problem is self-organizing system often operates in a very narrow range of parameters. Just to show you an example, these are the same army ants. Essentially what you have here is their ability to change direction, so to avoid other ants while they are moving along the trail. And that's, how do you call it, a politeness factor, right? So if you're here, like if you're on this side, you weigh the movement of the other individuals more than you weigh your own priorities. And if you're here, you weigh your own priorities more than you weigh the priorities of the others, okay? And what you can see in this particular case on this army ants model, there is a very narrow band of parameters, like the army ants are around here, where they are, and for which the traffic, the ant flow is very, very high. As soon as you deviate a little bit, as soon as you're too polite or not polite enough, very quickly things turn, you know, I don't want to say bad word. I live in New Jersey, so I'm used to swear. But, you know what I mean. And that's exactly what happened with us. One of the major problems of our US economy, this costs more than $300 billion a year to the US economy. Right? Traffic jams is terrible. This is Los Angeles, which is #1 worst city in terms of traffic jam. New York is #2. We're fighting with Los Angeles for the spot for #1. And just to show you how bad it can be, this is a situation, this 2 simulations, exactly the same parameters, except here you have polite drivers, and here you have like New York, New Jersey drivers. And you will see very quickly this situation is going to remain stable, and this is going to change. And the only difference is, by polite, I mean the individuals are trying to optimize their own behavior rather than trying to optimize the behavior of the group, and that generates this sort of these traffic jams out of nowhere. There's no reason for these traffic jams to emerge, yet they are. All right? And then we can go on. Fake news, rumors, crash in the stock market. All of these are problem with self-organization, right? Where we end up in this like bad situation. Now, even in the case of my beloved army ants, right? I'm going to show you a video. The only difference between this video and the next one is that in this case the traffic is on top of the bridge. In this video, the traffic is at the bottom. All right, this is it probably started attached to the ceiling, probably detached from the center, and because the traffic happens to go through the bottom of the bridge, and they tend to attach when they arrive at the bottom, this thing is elongating and elongating and elongating forever for absolutely no reason. All right, extremely wasteful because it's outside of its normal efficient parameter range. All right, what can we do? can you give me 1 more minute to, you have 1 minute to solve all these problems, all right? How can we escape these self-organizing traps? Can we do that? Well, I'm going to explain this, how we can do that, I'm going to stay in the context of traffic because that's where it's been the best study. So remember this situation. It's the same situation. The only difference is they are less polite here, okay? Now, the reason why traffic jam appears here as well is because so that's called the fundamental diagram. We look at the flux of car versus the density of car on the road. And I set my simulation exactly at what we call the critical density. This is where you maximize the flux. The problem at this point is where also you maximize the interactions between the cars. As soon as you maximize interaction between the cars, if one car slows down a little bit or prevent another one to go at its maximum speed, it's going to slow down, increasing locally the density. And if you increase locally the density, you increase the number of interactions, and increasing more the density, increase the interaction until you get into a traffic jams, okay? So I set my simulation here, and I created a perturbation in the system, and this perturbation brought the system to its knees, okay? Now, how do we solve that problem? There's 2 solutions. I'm going to give you number 2, which is, I think, not necessarily the best one, and a lot of people are going to disagree with me on this one, which is trying to maintain the parameters of the system in a desirable range. And we can only do this by actively regulating the behavior of the agent in the system. And that's the technological solution to it. And that's what you see when Google is trying to tell you, now, if you go this way, it's slower, you should probably go this way. So trying to change your behavior to optimize the amount of traffic on the road, or what's going to happen in a few years when we have these fantastic self-driving cars, where we're going to try to have these driving cars drive as close as possible, essentially try to minimize the amount of space they take on the road to minimize this possibility of traffic jams. Also, they are smarter than us and more reactive than us, so that might work. But there's another way to do things, and the other way is to keep the system away from these catastrophic conditions, okay? And this is by simply reducing the system's complexity. In the case of a traffic jam, it's really easy, right? We want to essentially keep our density of car away from that critical density. And public transportation, I know a lot of people are going to hate me in the tech valley, but public transportation is the #1 solution to traffic today in our cities. And it's the #1 problem to all our problem of self-organization. Right? It's a problem limiting the amount of information you get from social network. And limiting all these things is probably the only way to stay away from these problems without having to resort to complex technology. So I'm going to let you with these thoughts. And if you want to know more about my lab and me, you can contact me and all these different things that we do. They don't have time because I'm already late. Thank you.